This is a brief introduction to linear feedback shift registers for pseudo-random signal generation and some very simple tests. It's not meant to tell you everything you need to know. You have to look things up. Okay. So anyway, here's an introduction to what they are, right? We have a linear feedback register link from Wikipedia, and these are just flip-flops chained together, and then you have a feedback network. And what it is it can look like a random signal when a quasi-random signal is needed, but it is deterministic. It will repeat. And if you know what it is, what the random signal is, you can kind of hack or decrypt signals encrypted with this very easily. So this is not for encryption. This is more, let me generate a random set where I can send it in to test memory and read it back out. And so it's very easy to see if something has changed. All right. So you need to read up on that to understand. Anyway, here's some Python code to generate what looks like a random signal. All right. And this is 16. So the number of clock cycles before it repeats, it's easy to calculate. It's 2 to the 16th minus 1. All right. So every 65,000 clock cycles or events, this will repeat. And you can, you might try to find patterns, but it's kind of hard to tell. All right. Now, looking here, now we have a pseudo-random bit stream of two flip-flops. 2 to the 2 minus 1 is 3, so it should repeat every 3. So, you can see it's high, low, high, and you can just see that it's repeating even by eye. You can tell that that signal is not random. All right. Now this signal here has 3 flip-flops, and so it repeats every 7. And here's 4 for 33, right? And so I see this kind of medium, long, short, longer sequence, which kind of looks like that. So you can almost by eye pick it out. M to the 15, right? Now we're looking at 32,000 clock cycles. It's going to be very hard to figure that out by eye. Okay. So then there's 1 to the 31. And so we actually made a chip that will do that. And you can see, what is that? 2 billion clock cycles. All right. So that's that, right? So that's a very long sequence. And a lot of things that we're working on with stochastic computing and stochastic resonance, it just has to look random. We're not, like I said, we're not encrypting anything. So what are some tests that we can do though to see if it's random or not on a large data set? All right. Well, there's a whole, let's see, oh, here we go. NIST has all these tests, right, for random signals, okay? They even have a C code that you can download and you could probably import fairly easily into Python or whatever you want to do. Anyway, so if we take these signals like a, 1 or 0, it's like a coin toss, right? And the probability of a heads and the probability of a tails should be the same at 50, right? And if we assign 1 for heads and 0 for tails, the average, right, plotted out over time should be 0.5. In truth, if you measure that, it should approach 0.5, but depending on, your startup, it won't reach it exactly. Now, yeah, these notes are pretty rough. There's a lot of typos, but we're in a hurry. It's a research project. So if we look at the plot below, right, I'm plotting the average up to that point. Okay, so this is a 31 flip-flop linear shift feedback register, and we went for 10,000 clock cycles. So there's the data and time, and the orange is the average, right? So here, if I take the average of the 2,000 points, right, it's, what was that, around 0.8. Now, yeah, it's initialized to 1, right? And then after 10,000, yeah, it goes to about 0.4. So it's not going to 0.5. So it's not a fair coin toss, but on average, you're going to get more zeros than ones. You can still use this in stochastic processing, though. So that's one simple test. And what you can do is just flip a coin 100 times and plot the average with each additional point and see what it goes to. Then start again, do another 100 points and plot the average starting at 0. See if you get the same value of your final value. All right. So now there's another test, like, is there any hidden frequencies in your data? Right? Anything that repeats over time is not random, and like a sine wave, right? Now there's something called the fast Fourier transform, and that's really like a prism for data. So a prism takes white light and gives you how much red, yellow, and green, right, that you can see. A fast Fourier transform will give you what frequencies are in your data, right? Now, there's a lot of theory for that, but it's relatively easy to use. And then, looking at, what we see. So here is, we have our 3 flip-flop pseudorandom bit stream generator, and we're going to go for exactly 7 clock cycles. And so if we were to go more than that, it would start to repeat. And then we take the FFT, and we have a DC average, and then it just flattens out. Now this axis here is frequency, and the period is 1. So the base frequency is like 1 over 1, right? You just multiply it by the actual frequency of the clock, and that will work. So this is it's all the same period. I'm assuming a period of 1 second. Okay, now let's run it 21 times, right? You can see the pattern repeat 3 times. Let's take the FFT. And now we're starting to see peaks, okay? Indicating that there's a repeating pattern in there, right? Let's run it for 70, right? And now there's definitely 3 strong peaks. You can see the magnitudes change depending on how much data you take, but there are 3 peaks there. It's telling you that signal is not random. Now let's just try, what would it look like I'm going to let it go for a longer time, right? And the clock cycle's not being divisible by 7, all right? So that's a very long time. And because it's not divisible by 7, you get this smoothing. But notice the peaks are still there. Something I have to look into is that the average, this peak here is DC, and that should represent the average of the whole signal. The average should not be above 1, because if the data can be 1 or 0, the average of that cannot be greater than 1. So I must have a typo somewhere, right? But regardless, you can see these peaks, right? And even if there was a DC average, you could subtract that out and, it would be then you could see your frequencies, right? So, um, on any group of data, you can take a fast Fourier transform of it. The ADLM 2000 allows you to do that. And when you're looking at the oscilloscope, if it's small enough, if the pattern is small enough, you can see it. But if you start to see these peaks, right, that means something is repeating and it's not random. And again, this is a pseudo-random bit stream generator, not a random bit stream generator. You need true entropy to do random signals. And there's circuits that do that, but surprisingly, you have to be very careful with it. There's other random signals where you just look it up in a book. Somebody's effectively done that toing cost for you, and you just use a book and or encode it, or I bet it's online somewhere by now. But for encryption, you need true randomness. Anyway, hopefully that's enough just to get started. Forgive all the typos, but that's just enough to get going. If you want to know more, you really do have to look through the theory of the Fourier transform, and for the for the linear feedback shift registers, you have to, draw the flip-flops, draw the logic gates, and see what happens cycle by hand, right? For instance, set all of these to 0. All right, what is going to happen, right? Well, if this is 0 and that's 0, that XOR makes 0, right? And so if this so 0 XORed with 0 makes 0. And again, this is starting all off at zeros, right? And if I put 0 with that 0, I get 0. And what happens is it continues zeros. Nothing happens. All right. So I use XNOR, right, many times and start with zeros. But if I put all these flip-flops to a high level, right, I get 1 XOR with 1. That makes a 0. That would be 1 XOR with 0. That makes a 1. And then 1 XOR with that makes a 0. So it starts off a 0 pattern, but eventually it will start to kick in. And you can randomly see this as well. Okay? It's much easier to look at it for 3 flip-flops or 4. So it's a lot easier. Okay? In PSOC, they actually have a part. This is bonus material. They have a part that you can configure, and how many flip-flops, right? What is the seed value, right? You can arbitrarily do whatever you want with that, okay? Or you can, let's see, doing another project. Anyway, that's enough content for one day.